Welcome back. Today we are going to solve this question over here. We have an information of a patient who is a GH, who is a 70-year-old female patient. Height is 5 feet and weight is 120 lbs. And the serum creatinine is 1.5 mg, fraction excretin change is 0.75, and the CSS average in normal patient is 1 micro. In this patient, the required dosage regimen that target CSS average is 1 microgram per liter, and the bioavailability of the tablet is given by 0.75, and the clearance is 11.3 liters per hour. The T half is 36 hours. This is a normal patient though, okay? So remember that this is a normal patient. Alright, so these are the following things that we need to estimate. Okay, what's the first thing that we need to calculate if we have to calculate clearance? We need to calculate creatinine clearance, right? Okay, what's the equation for creatinine clearance? Cochran-Gault equation, right? CNG equation. So it's 140 minus age times weight in kilograms divided by 72 times serum creatinine. Are we missing something here? I think so, right? Because it's a female patient. She's a female patient, so we have to multiply this entire factor, by 0.85, 0.85. All right. Okay, so let's plug in the values here. So we know the age is 70 years. Okay, weight, so 120 lbs, but we need to plug in these values in kilograms. Okay, let's convert this into kilograms. How much is that? 120 lbs is 54.55 kilograms. But I hope you remember our previous video, which I posted in my Blogspot, the weight considerations in Cochran-Gault equation. For this particular patient, we have to consider the ideal body weight, right? So the ideal body weight for this patient is 45.5 kilograms. So let's plug in now. So it's 140 minus 70 times weight, it's 45.5. divided by 72 times serum creatinine is how much? 1.5 mg per deciliter times 0.85. If you solve this, you'll have a value of 25.07 ml per minute. Okay, this is the creatinine clearance. And what is the normal creatinine clearance value, by the way? It's 125 ml per minute. Right, so this is the estimated and this is the normal creatinine clearance. So the renal function, the RF, so the RF that we're going to calculate, it's patient's creatinine clearance. Okay, patient's creatinine clearance divided by normal clearance. So that is patient's is 25.07 ml per minute divided by the normal clearance is 125 ml per minute. So if you solve this, we'll have a value of 0.2. There are no units because we're going to cancel the units over here. So now that we know the renal function, let's calculate the renal fudge factor. Okay, and the renal fudge factor, it's okay, before we discuss the renal fudge factor, let's look at the clearance of a patient, how we calculate. So this is clearance of the normal patient is equal to clearance of the normal patient, okay, times 1 minus Fe times 1 minus Rf. Okay. Alright, so let's plug in the values here. The clearance in normal patient, which we already mentioned here, is 11.3 liters per hour. It's 11.3 liters per hour. 1 minus the fraction excretin unchanged 0.75 times 1 minus the RF, the renal function, that is 0.2. Okay. Okay. What I'm going to do is I'm going to just calculate this particular part. Okay, and I'm going to call it as renal fudge factor. Okay, So 11.3 times 0.4. Okay, if you solve this entire equation, you'll get a value of 0.4, by the way. Okay, now if you multiply them together, the new clearance, and the clearance in the patient is 4.53 liters per hour. Okay, now that we know the clearance, we can calculate T half, your dosing regimen, everything, dosing rate, dosing interval, etc., etc. All right, the next thing we need to calculate is we calculated clearance, right? We calculate creatinine clearance and the renal function. Now we have to calculate dose rate. Let's calculate the dose rate. Okay, I hope you remember the formula for the dose rate. The CSS average is equal to bioavailability times the dose rate divided by the clearance of the patient. Okay, all right. So the bioavailability, as you're aware, the CSS average is 1 microgram per liter. Okay, it's 1 microgram per liter, and the bioavailability is 0.75. 0.75 times the dose rate, that's what we're going to find out, divided by clearance, it is 4.53 liters per hour. Okay, now if you rewrite this equation, dose rate, okay, we're going to calculate the units, liters cancel, and we're left with microgram an hour, so it's microgram per hour in dosing rate units. And if you solve for this entire, you will get a value of 6.04 microgram per hour. Okay, so it's 6.04 micrograms for 1 hour. How much is for 1 day? 24 hours. Okay, if you solve this, then we'll have a value of 144.91 micrograms per day. All right. So now the next thing is calculated the dose rate. Now the next thing is we need to calculate the T half of this drug. The T half of the patient is T half of the normal patient divided by the renal fudge factor, that is 1 minus Fe times 1 minus Rf. Okay, so this is why we have calculated this here, renal fudge factor. I hope you remember this. Okay, I hope you remember this one, the renal fudge factor. We calculated this earlier. So T half of the normal patient is around 36 hours, I believe. Yes, it's 36 hours. 36 hours divided by the renal fudge factor, that is 0.4. Okay, if you solve for this one, the T half of the drug in the patient is approximately 89.91 hours. So roughly it's 90 hours, right? Okay, now we have to calculate the dose interval. Okay, most probably the tablets are available in the form of 125 or 150 or 250 mg per mg, right? So obviously when the tablet is available in the form 125 microgram and 250 microgram. So we recommend, to maintain a CS average like 1 a day tablet of 125 microgram, per day. Okay, so let's leave this apart about the numbers and numerical values. Let's find out why there is an increased clearance. Obviously, digoxin is cleared renally, and from this information here, the renal function information over here, the renal function is 0.2. That means 20% of the nephrons are working effectively in this patient. Okay, so what does that mean? That means only the drug, usually if it's clear 100% in normal patient, now because only 20% of the nephrons are working properly in this patient, it's able to clear only less amount of the drug per hour. So there is a reason why there is a decreased clearance you noticed an increased T half in renal impaired patient. Okay, so that's all for now.